Vamos a iniciar. Buenas tardes a todos, mi nombre es Fernanda Moya y como presidenta de la Academia Estudiantil de Investigación Geocientífica de la Universidad Mayor, le agradecemos a todos la participación y motivación en el desarrollo de nuestra Semana Geológica. A continuación tendremos una charla dirigida por Felix Boschetty, es petrológico y interesado en comprender la dinámica de la arquitectura magmática y actualmente estudiante de doctorado en la Universidad de Leeds, en Reino Unido. También está estudiando el sistema volcánico del Volcán Villarrica, acá en Chile, y utiliza diferentes herramientas para comprender el almacenamiento y la evolución y transporte de magmas en sistemas volcánicos. Esto incluye composiciones de vidrio y minerales contenidos en inclusiones de composición vítrea y disonaciones de minerales. Actualmente se encuentra trabajando en el uso de técnicas de Machine Learning para analizar grandes conjuntos de datos en composiciones de minerales. Entonces le damos el ingreso a Felix Boschetty. Muchas gracias por participar y las preguntas y respuestas se van a dar al final de la charla. Pueden dejarlo en el casillero mientras se va realizando la charla. Eso, muchas gracias.
Thank you very much. So yeah, I'm going to speak English. My Spanish is very basic, so I hope that's okay. So today I'm going to talk to you a little bit about maybe some slightly less conventional techniques to look at igneous petrology. And I guess just to start, I'd like to highlight that just because I'm the one speaking to you, this work wouldn't be possible without all the other work from the other people involved, both here in Leeds and in Chile, Eduardo, Jorge, and Carolina especially. So yeah, today I'm going to talk to you a little bit about the work I'm currently doing on Villarrica. I'll try not to patronize you about the beautiful volcano that exists in your country. So to kind of start off, I'm going to talk a little bit about Villarrica, just as an introduction, and then talk about sort of the questions we're trying to answer. So Villarrica is an active stratovolcano in the central South Volcanic Zone in Chile. It's the red volcano here. It's one of the 7 volcanoes in the world currently that have a lava lake, and this means that it's constantly got a supply of magma to the surface. And in part because of this, it's considered one of the most hazardous volcanoes in Chile by Semana Geológica. And it's had over 50 eruptions in the last 500 years. And importantly, as you can see in this picture on the right, there's a summit glacier. And when lava interacts or tephra interacts with the ice, it makes it very dangerous because you can have lahars. So the most recent eruption came in 2015, the most recent significant eruption, the aftermath of which you can see on this upper image, and you can see all the tephra that came out of the top of the volcano. And this eruption was quite explosive. It produced a 1.5 kilometer high fire fountain, which is sort of unheard of for Villarrica, at least historically. But this is, when we're talking about really all the eruptions of Villarrica, this is still quite small. In the past, it's erupted much more violently. There's been 2 very large mafic ignimbrites that produce 10 cubic kilometers and 5 cubic kilometers of material. So it would have blanketed the whole area in this image, in substantial thicknesses of material. And at the same time, on the sort of an average day at Villarrica, there's this sort of minor eruptive activity happening around the lava lake, maybe strombolian. So there's a big range of eruptive styles at Villarrica, from really big explosive ignimbrites to a lot smaller but still significant historic eruptions like the March 2015 eruption, and then this constant bubbling away of the lava lake. But despite this, the range of compositions of lava and tephra that come out of Villarrica are quite consistent. This is a plot, and this was 14,000 years worth of data on it. And the majority of the material has a very limited silica content. We're very much in this basalt to basaltic andesite range. So if the composition of the erupting material isn't changing a lot, what's driving this big change in eruptive style? What's making the difference? What causes Villarrica to potentially erupt in a spectacular fashion versus just bubble away quietly? And this kind of gets onto the sort of big question that we're trying to answer at Villarrica. And one way to do it is maybe not to look at the whole rock compositions by themselves, but to look at the composition of minerals that erupted at Villarrica. So one of the best tools to understand a magmatic system, in my opinion, as a petrologist, are the minerals that get erupted and that we find after the eruption. So, you know, a lava or a tephra contains a lot of crystals, or can contain a lot of crystals. And these crystals can come from various places and various times. So there are what we call autocrysts, sometimes called phenocrysts, which come from the liquid which is erupted at the surface. So at some point in its path of the magma through the volcanic system, it crystallizes these minerals, and they're called autocrysts. Then we have something called an anticryst, which, as the name would suggest, crystallized before the liquid got to the system, and they get picked up later. We may also have xenocrysts, which are foreign in some way to the magmatic system, and we can have microlites, which crystallize after eruption. And sort of combined, all these crystals can give us an information about the magmatic system. You know, you might say that an eruption gives us a partial snapshot, gives us kind of information about what some of the crystals are like in the system and how they're interacting. And if we have many eruptions over a period of time, as we do at Villarrica, you know, potentially hundreds of eruptions over the last several thousand years, we could take all of these eruptions and all these crystals that have been erupted and put them together and tell us something about the system over time. So as I just said, Villarrica has had lots of eruptions and still erupting. Unfortunately for us, there's been a lot of work done by previous students and academics on Villarrica, and they have recorded the composition of the minerals that have been erupted and said something about them. But no one's really looked at lots of eruptions, or many eruptions, more than a handful, and compared them. So this is kind of what we're attempting to do. We're trying to synthesize a lot of data and bring it all together and say something about Villarrica. So we have all these data that people have put together in the past, and specifically there's from about 20 eruptions, and there's a big range in time, from approximately 100,000 years ago all the way through to the March 2015 eruption. I will say that the majority of the eruptions that people have looked at are, not surprisingly, historic eruptions. They're eruptions that happened in the last 100 or so years. So you can see in these pie charts, the historic eruptions, those that erupted in the last since 1921, make up the majority of the data. And that's all that you really need to kind of think about. So we're going to look at the mineral compositions. We're not going to look at whole rock or glass. Why not? Well, whole rock, we already know, is quite similar throughout the eruptions. And it might kind of hide sort of more subtle or smaller changes or smaller differences that we might be able to detect otherwise. And glass, well, glass is the glass that comes out of the top of a volcano in a lava, or more likely in a tephra, really only tells us about the very last things that are happening. They only tell us about the liquid that's present right before eruption or during eruption. And we're trying to look at what's happening deeper in the volcanic system. So that's why we're only looking at mineral compositions. So we have 2,678 analyses to look at. And these are divided between the most common minerals that are erupted at Villarrica: olivine, plagioclase, and clinopyroxene. And we have a significant number of analyses. This is not unheard of. I mean, there are plenty of other volcanoes around the world, Etna, for example, that have a lot of previous data, but Villarrica, importantly, especially in Chile, is one that people have studied quite a lot. And these data are sourced from published analyses, from some of my colleagues haven't published analyses yet, but they've we've sort of looked at them, and from theses like Jorge Clavero's thesis, a lady called Silke Lomar, and some of my other co-authors. So we have all this data, and we'd like to look at it in some way. And we actually have quite a lot of data. We have almost 3,000 analyses. And I'm sure you can imagine that if you were to go through nearly 3,000 analyses individually by hand, trying to compare them, that might take a very long time, and two, be quite difficult. So here is kind of where the machine learning aspect comes into play. We have what is machine learning? Well, machine learning, it sounds very complicated and difficult and hard to understand, and it is to understand exactly what's going on. But really, it's just some computer program. It's an algorithm that finds patterns in data. That's what it tries to do. And the type of machine learning that we use is cluster analysis, and this basically attempts to find similarities between data. So on this right-hand picture, you could imagine that if you had all of these points and they're not colored, you could maybe by eye group them and say, okay, these ones are kind of close and similar. We'll put those in one group, and same with these, and same with these. And it's not too difficult to imagine being able to do that with not lots and lots and lots of analyses, and in only 2 dimensions. Here we're just looking, we have some measure between 0 and 1. But it gets a lot more complicated when we're trying to compare data with more than 2 dimensions. With 3 dimensions, we could maybe do it by eye. But beyond that, it becomes really difficult. And that's where machine learning kind of comes into its forte, because it can look in hundreds of dimensions. These sort of algorithms can look in thousands, hundreds, even millions of data points with hundreds of dimensions and find which are more similar or not. So to kind of understand how we went about it, if you imagine olivine, it's a magnesium silicate mineral, and it's basically made up of iron, magnesium, and silicon oxides. And in this case, we kind of threw 2 minor elements, magnesium and calcium in. But if you imagine an analysis of olivine, it could have 5 dimensions: magnesium, iron, silicon, manganese, calcium. So these are the sort of 5 dimensions that we're looking at the composition of these minerals in. And we can do the same for plagioclase, we can do the same for clinopyroxene. They've got different mineral structures, so they're slightly different, but that's essentially the way we're looking at the data. So the to kind of give you an idea of how the analysis works on a sort of more basic level, there's a GIF, and it's gonna play, and we're gonna go through it a little bit by bit. So if we had 6 points, 7 points rather, when they look something like this, what hierarchical clustering, what the method that we use attempts to do is it groups the closest, the most similar data each time until there's no data left, or everything has been grouped into one. So in this case, it's going to group the 2 closest data, 5 and 6, and it's going to say, okay, they're the most similar. We're going to treat them as one point, and then it takes the next 2, and so on and so forth. And if I click up here, you should be able to see. Okay, so if we were to stop now, you could count. We have 1, 2, 3, 4, 5 clusters, and that's telling us something about the system. It's saying that the 3 points that make up this cluster are the most similar, and these are kind of at this point treated as less similar. We can go through and do the same, getting each time grouping the most similar points until everything's in one cluster. We've grouped them all together. And what we've done is we've recorded the distances between the points here, and we've grouped them in something that's called a dendrogram. And it's a lot of detail, but it doesn't really matter. It's just kind of give you a feel for what we're doing. We're grouping most similar points and building them up and building this tree. And then we can look at the relationships between these data recorded in this way. And we can conveniently draw a line across at a point that we deem as significant and say, okay, we can group our data. It falls into 3, 4, 5 groups. So we did this for each of the data sets, and for olivine, plagioclase, and clinopyroxene. And importantly, I should sort of emphasize that when we started to do this, we weren't particularly hopeful. The fact that it worked was a surprise, and it worked surprisingly well. So, as I said, olivine is 5-dimensional, plagioclase was 8-dimensional, clinopyroxene 10-dimensional. And dimensions are kind of the elements that were analysed. So for olivine, silicon, magnesium, iron, calcium, manganese. Plagioclase, silicon, aluminium, sodium, potassium, calcium, magnesium and iron, etc., etc. So we've got this multi-dimensional data. On the right, what we're doing is we're viewing it in 2 dimensions. We're taking the data and we're taking this complex data and we're flattening it so that we can look at it. So that's what this plot's showing. It's showing the identified clusters with the analysis, and it's colouring them in. So yellow, all the yellow points form one cluster or one group of olivine compositions that are similar. Green, likewise, turquoise, and blue. And so we identified 4 clusters for each of the minerals. And I should point out that this is a coincidence. There doesn't have to be the same number of clusters for each mineral. This could be 3, it could be 1, it could be 10. It just happens that there's 4 for each. And yeah, there's good separation in that. In generally, all the yellow points are together, all the green points, all the blue points, and the same really for all the minerals. It gets more complicated the more elements you look at, but it worked. And to kind of represent each of these clusters, we have this red point for each one of them. And this is the composition that we use to kind of describe the whole group. So if we look at the compositions in a different way, or the clusters in a different way, in grey is all of the data, all for olivine, all 800 points, for plagioclase, all 1300 points. And we're plotting them against some measure of evolution. So this is Forsterite number for olivine, which is a ratio of magnesium to iron, and the most primitive olivines have the highest ratio, the highest number here. For plagioclase, it's an orthite content, and clinopyroxene, magnesium number again. But the point of these diagrams is to show that if you were to look at just all of the data all at once, we haven't done any analysis to it, we've just calculated this number for every point and plotted the distribution of them, you might think that there are 2 main compositions. There's one represented by this grey peak here, about 80 something, and one here represented by about 75. But if you were to look at the clusters, the clustering analysis that we did, that takes into account all of the elements, we find that it's a bit more complicated than that. And the same is true for both plagioclase and clinopyroxene. So this is the advantage, this is the strength of our analysis. It allows us to see things that you might otherwise not see. Okay, so that's good. We've taken these large number of analyses, and we've found similarities between them, and we've grouped them based on their composition. So what does that do? What does that allow us to do? Well, the next thing that we kind of want to do is relate these to the system itself. Where are these crystals forming? Is there a pattern in where they form? And what can this tell us about the system itself? So to do this, we have to make our own volcano. We have to make a very simplified system and change things and see what happens. So we're simulating a magma chamber, and it's a blob of magma. And initially everything's liquid, and then we cool it down. And as we cool it down, crystals form, and we could imagine that they might sink. They're heavier than the liquid. They might sink to the bottom of our magma chamber and then just sit there and not interact. So that's what we're doing here. We take a blob, crystals sink, and eventually we've cooled the system enough that it's all solid, and we stop the simulation. So this is very, natural systems. Volcanoes are a lot more complicated, but this is just something that we can use to see, is our grouping or our compositions, does that mean anything? Is it meaningful? So we ran a bunch of these fractional crystallization models, and we used realistic conditions. And so we start with a composition that has already been recorded at Villarrica, and we run it a whole different bunch of pressures, water contents, oxygen fugacities. We ran 1,500 simulations. So we ran a lot of simulations, which was quite intensive. And then what we want to do is compare the simulated mineral compositions and compare them to the compositions that we found from clustering, and see, do they match? Can we reproduce these compositions? And if so, is there any difference between where we find one olivine cluster and the other olivine cluster? Do they form under different conditions? And the answer is yes, they do. So without going into lots and lots of details, we find something interesting. Notably, there's a big range in pressures between each cluster, and the simulation that best fits them. We find that things crystallize near the surface, but also all the way down 10 kilometers depth, all the way down to 22 kilometers depth. And that's interesting. It kind of is different to what's been traditionally said about Villarrica. Often people talk about a shallow storage region about 5 kilometers depth. So if we compare it, it's quite busy, but if we compare it to previous data, this is from the studies that we took the data from, they suggested that lots mostly crystallize around 5 kilometers. There's some at depth and some even further than we found, all the way down, potentially near the base of the crust. So the fact that there's an agreement here suggests, again, that our analysis is good and meaningful, and that even though we're using a very simple simulation, it fits, it makes sense. There is a temperature difference, but that is likely because our system is just a little bit too simple. In reality, we know that there's constant supply of magma through to supply the lava lake, and that keeps things probably a bit hotter than in our simulations. So now let's have a look at this cluster here. It's a bit of an oddball. It's quite deep, it's quite cold, and it's significantly different to the other results that we got. So this is where we start getting numbers, and it gets a bit even more dry. So I'll try to be pretty quick. So this is plagioclase cluster 4, and that's this square down here that we think crystallized deep and cold in the crust below Villarrica volcano. This is cluster 1, a different plagioclase, just for comparison. It has a lot lower anorthite number, which suggests that it crystallized in melt that had sat around for a long time. It had crystallized other minerals before it to a higher degree than this cluster here. And in fact, it's in equilibrium with a high silicon melt, about 61 weight% silica, which is relatively high. And the simulation suggested that when it formed, about half of our magma chamber was full of crystals. And yeah, just for comparison, we're talking longer temperatures, which you might expect if this magma chamber had sat around for a long time, higher pressures, and still at reasonable water content. So that the sort of story here is that to produce this sort of crystal in Villarrica, the magma that it's crystallizing from would have to sit around for a significant period of time. And it would end up being quite crystalline. And sort of another important thing is that this cluster 4 plagioclase is limited to the oldest eruptions at Villarrica that we looked at. So this is a dacitic dome that's about 100,000 years old. And then the Lican and Pucón ignimbrites, the most explosive eruptions recorded at Villarrica. And only those 3 eruptions have this group of plagioclase in it. So we're talking about a high crystallinity, and as you get more and more crystals in a magma, it's harder to erupt it. So this is kind of important, because if this type of plagioclase were to make it to the surface, as we know it must have done, because someone has analyzed it, something needs to change about this magma to erupt it. And commonly we think that it would require fresh input, fresh magma from the mantle to interact with this, to carry it up to the surface. And the fact that it's found only in the 2 most explosive eruptions is interesting. Could there be a link between this composition of crystal and explosivity? Do we need to generate an explosive eruption at Villarrica? Do we need to have magma that sits around for a long period of time and produces these different composition feldspars, and then something must happen to it? Does it get rejuvenated? Does it get triggered by primitive magma coming in? And could this explain why some eruptions at Villarrica are more explosive than others? So to kind of bring some of these ideas together, because there's an active lava lake at Villarrica, we know that some magma must go through this volcanic system quickly. If it never made it to the surface, we wouldn't have a lava lake at the top of Villarrica, and we wouldn't have degassing. We wouldn't have sulfur coming off the top of the volcano, which you can see pretty commonly. But we know that some crystals must spend a lot of time in the system if our analysis is correct. But despite spending a lot of time in the system, the magma becomes increasingly sticky and harder to erupt. Something must carry it to the surface. Something must erupt it. Otherwise, we wouldn't be able to measure it. And potentially, the fact that it sticks in these, it's found only in the most explosive eruptions, potentially highlights that this process from whatever the process that allows these crystals to be erupted is responsible for these very explosive eruptions. Where are we? So I've gone quite fast, but I'm hoping that there'll be lots of questions. So thanks for listening so far, and hopefully people will have questions, and I'll hopefully be able to answer them. Thank you very much.
Thank you so much, Felix, for your presentation. Vamos a iniciar con las preguntas. Pueden dejarla en la caja de preguntas y respuestas o en el chat. Nos llegaron por interno algunas preguntas, por mientras las vamos a hacer. Un segundo. Acá hay una. Pregunta anónima. Dice, ¿pudiste encontrar diferentes composiciones de minerales en una erupción o las erupciones estudiadas son relativamente homogéneas?
Did you understand, Felix?
I understood the first half. Could you enlighten me on the second half, please, Eduardo?
Okay. What happened is, if you could find in one single eruption different mineral compositions, or for example, one eruption had, for example, forsterite something, forsterite 70 and the other forsterite 50 only, or the products were generally mixed? Because, yeah, I mean, I think that question makes sense because you were showing a lot of different groups. So
okay, so is the question, let me go back. Is the question asking, are these groups found only in one eruption or in lots?
yeah.
Okay, cool. So the answer is lots. So these crystals are found in, you can see this. Yeah, so the crystals are found in, basically all crystals are found in all eruptions. Almost. There are trends, but yes, in general, all of these crystals or groups of crystals are found in some proportion in all of the eruptions. So if we look at olivine along the top, this is plotting different eruptions, but basically the oldest is on the left and the youngest is on the right. And through time, the proportion of crystals that are erupted changes. So the Liccan ignimbrite, which is very explosive, has a different proportion, say, to in 2000, which was very non-explosive. And by looking at how this changes through time, we can potentially relate this to the eruptive style. Hopefully that answers your question.
I think, yeah. And I have a question too.
Yes, Eduardo.
For your model, first of all, it's very interesting you're showing, for the first model I have seen in Villarrica, this kind of polyvariate crystallization, showing different levels, forming different crystals, rather than what we usually did. As you said, it's like, okay, let's use this thermobarometry method, and then we're going to guess where exactly that, for example, that figure. And I was thinking about the model by Dufek and Bachmann, 2010, like quantum magmatism. And maybe I would like to know if you have thought on the possibility of, for example, if you have a high crystallinity magma, the possibility or no, the probability of magma extraction increases. Maybe you remember that article? And
yeah.
if you have thought about it, I mean, because to form that crystal, you need high crystallization or high crystallinity. And have you related your own model with that model by Dufek and Bachmann? Sorry.
A little bit. So yeah, you're right. I guess starting super basically, I think the assumption that a lot of people make when they look at an eruption is they say, okay, these crystals formed from the liquid that is erupted. And I think what's becoming more and more clear is just because a crystal came out, in fact, you'll know this very well, Eduardo, because you look at timescales. Just because a crystal was erupted at say 20 years ago, doesn't mean that it wasn't crystallized and formed initially 5,000 years ago. There's no constraint there. In terms of so I guess if I go back to my cartoon, just because so if we have this deep reservoir or some sort of system that's deep, I think things can sit there for a very long time before they potentially come out the top of the volcano. And I think that's kind of shown by this. We find this plagioclase only in we only can go far back as the eruptive record, but 1,000 years, 13,000, 14,000 years, and 4,000 years. Those are the only three eruptions that have that. It's not present. So there's something has to bring this up and drag this out. I agree that the mechanism is probably quite complicated, maybe quite complicated, because when you get to these high crystallinity magmas, things get a bit weird. But I think I think this suggests that this is probably taking place at Villarrica. Maybe not necessarily at this, it might not be as distinct as, you had a crystal that sits around for 10,000 years before it's erupted, but I think that it kind of suggests that this polybaric type stuff definitely going on.
Yeah, no, very interesting, and congrats.
So I can see there's a question about why I chose Villarrica, why not another volcano, and why Chile. Yeah, it's a good question. I chose, well, my experience with Villarrica is long. I first came to Chile. I got to spend some time in Chile in 2014, and I went to and saw Villarrica then, and I've been back once since. And I guess it's a very interesting volcano, one, because it affects quite a few people. There's a lot of people who live in Volcán and Villarrica and around it. And yeah, it's really interesting because it has this composition that doesn't seem to change, but it's has very different eruptive behavior throughout its history. And I don't think anyone really understands why. So that's kind of why I'm interested in Villarrica. Also, it helps, well, it doesn't help, but in England, we don't have any volcanoes, at least not any active volcanoes. So I'm kind of forced to go outside of England if I want to do volcanology.
Bien. Tenemos otra pregunta. Eduardo, si puedes traducirla. Coti Figueroa pregunta, tengo una duda, ¿los resultados son consistentes con las conclusiones de los trabajos que han sido publicados anteriormente?
Okay, are your results consistent with previous work, with the conclusions of the previous work related to Villarrica volcano?
So let me go back to this slide. In terms of the pressures that we and temperatures and depths that we got out of our modeling, yes, they're comparable in that we think that there's crystallization going on throughout the crust, and that's supported by past work mostly. I don't think, well, the idea that the crystallization is happening throughout the crust and that it might take place in highly crystalline reservoirs is a relatively new idea. Relatively, it's been thought about for about 30 years, and a lot of these studies happened, sort of started to happen in 2008. So perhaps potentially the ideas that we're talking about have kind of developed a little bit further. So I think they kind of agree, but I guess it's also important to note that we're looking at lots of different eruptions and not just one. And without looking at all of the eruptions, you probably wouldn't get the same story.
Here there is another question by Nushka, and is, how can you explain your shallow reservoirs, or according to your model, are not showing any mixing with the deep reservoirs, I guess, and what's the probability that those magma mixing are actually reflecting different stages of evolution?
Yeah, so I guess I kind of skipped over it a little bit and I wasn't very clear. So ignore the green. But I think there is mixing going on, and I think there's probably mixing going on all the time. And the reason I think that is because the whole rock composition at Villarrica is very consistent. And the only way you could have that there's two options. Either magma ascends and it doesn't do anything. It doesn't sit around at all. It literally comes from the base of the crust and comes out the top, and therefore it's always the same. I think we can say with certainty that's not the case, because if it was, it would be a lot more primitive. It would have a lot lower silica number. It wouldn't be 52 to 57. Instead, what I think is happening is there's crystallization throughout the crust, and magma interacts with crystals and drags them out of the whole system. And there's always some mixing going on at the top between more primitive and less primitive melts. And on average, that gives you about 52 to 57 output. But the point being that the magma could contain crystals from depth. It could contain crystals only from the shallow system. And there's something about the dynamics of the eruption and the magma that feeds that eruption that determines whether it has crystals that have sat around for a very long time or not. And that's kind of the question is what makes it so that there's interaction between reservoirs or parts of the system that haven't been interacted with for a long time, and what makes it so that it just trickles up through the top and you get a little strombolian eruption. So that's kind of, that is the big question. I think the amount of mixing plays a part, and future studies, potentially doing things that Eduardo does, looking at diffusion timescales, could help answer that question. Hoping that's
yeah, and that's another question by Raimundo, asking, like, he wrote in English, so I'm going to read. Related to prior question, is there another place in Chile as appealing for geological study as the Villarrica volcano?
Well, I'm very biased. I have a very strong opinion because I've spent a lot of my time that I spent in Chile has been in Villarrica, and I think it's one of the most beautiful places on the planet. But, and I'm sure you'll know better than I, but Chile has got beautiful places and very interesting volcanoes, faults. In terms of geology in general, I think Chile's pretty incredible. So I wouldn't say it's the best place necessarily, but it's the best place that I've been to.
Yeah, but for example, for the study you are doing, I think maybe Villarrica is the best place in South America and Chile, maybe because it's very active and it has been very studied. Very different, like research groups have focused on it. So that's why you have all those data. You know, you're getting your own data, but
yeah, in terms
of, if you compare with other volcanoes as Calbuco, Osorno, Mochochozuenco, for example, Villarrica has been like very studied, and that's why you get those compositions, mineral chemistry and whole rock chemistry. Maybe that helps. Raimundo?
Yeah, I mean, without that data existing, it wouldn't be possible to do this sort of analysis. So yes, in that case, yes, Villarrica is also very appealing because without it wouldn't be possible. But hopefully that will change, and more volcanoes in Chile will be studied in the same way, and then there's potential to do this analysis elsewhere.
We're trying. We're applying to different projects, so fingers crossed. If we get them, why not to do machine learning on the products of other volcanoes too? Or
maybe even machine learning on the products of all Chilean volcanoes. I mean, this is very small scale. I'm sure we could ask questions and try and answer them about the whole southern volcanic zone, for example.
Yeah, that would be perfect.
Me parece que hay una pregunta más en el chat de Martín González, también está en inglés. No sé si quieres leerla tú, si no.
No, sí, ya la discutimos.
Ya.
It's why Villarrica and why Chile.
Yeah.
Yeah, we discussed a few minutes ago about it. So.
Ok, entonces creo que estamos listos con las preguntas. creo. Hasta ahora no ha llegado ninguna. Así que vamos a dar cierre entonces a la charla. Muchas gracias, Félix, nuevamente por tu participación. Y bueno, te dejamos la invitación de participar en algún próximo evento con nosotros nuevamente. Ahí estaríamos muy felices de tenerte ahí. Y bueno, sí, la gente lo está pidiendo. Ahí Damián dice que sí, por favor. Y eso, más que nada, dejamos la invitación abierta y eso. No sé si hay alguna persona de la directiva que quiere comentar algo, o Eduardo, abre su micrófono.
Bueno, quería decir un poquito que en realidad esta es la primera parte del proceso de doctorado de Félix y se hizo precisamente en Machine Learning, estudiando los procesos, perdón, los productos ya estudiados del Villarrica porque estaba encerrado por la pandemia. Pero ahora está trabajando en obtener sus propios datos, eh, datos que no se han obtenido anteriormente, por ejemplo, hacer cuantificación de volátiles en inclusiones vítreas, que no se ha hecho anteriormente, y cosas por el estilo que seguro lo voy a invitar a presentar de nuevo porque de verdad es súper, súper interesante.
Sí, muchas gracias a ustedes para escuchar y sí, espero que en la futura tendría más resultados para share con todos. Sorry, that was.
We hope
bad.
too. But
Entendido, no te preocupes.
There's another question over there. Like, how was the study initially produced? Like, how was like the idea? I don't know. Maybe you can talk about it. How we met.
Well, initially, I signed up to do a project working on Villarrica, in a large part due to the fact that Eduardo had just finished his PhD, his doctorate in Leeds, where I am now. And I went to Chile last year and collected lots of samples, and then got back to England, and everything was shut because of COVID-19. So I currently have 60 kilograms of samples that have barely been touched because we've only just been allowed back into the university. So the sort of impetus of this was to look at data that already existed rather than data I need to collect myself.
Yeah, now the same Amanda again, the same said, like, I mean, what was basically the motivation to start this study for you, maybe?
For me,
guess. Yeah, I guess that's the question, no, or not? Because in the beginning of time, like, maybe for you, your motivation to study Villarrica, or our motivation to create this project.
Well, my motivation is it gave me an opportunity to come to Chile and see a place that I really love again. But scientifically, as we've said, Villarrica is just super interesting. And despite being studied a lot, there's still a lot of room, I think, to answer scientific questions about Chile, about Villarrica.
That's all, I think. I haven't seen more questions, new questions, so.
Thank you, Javier.
Bien, entonces ya vamos a dar cierre a la charla. Bueno, nuevamente agradecer a Félix y a todos los participantes por su motivación a estar en esta charla y bueno, seguir con la Semana Geológica, que ha tenido hartas charlas interesantes y todavía tenemos dos más. Una dirigida por Rodrigo Contreras, que se encuentra ahora, ahí pueden verlo en la cámara, que va a hablar sobre monitoreos, un poco de sismología, así que ahí les dejamos invitados a participar. Y ya en la tarde a las 5:30 tendremos nuevamente otra charla con Matías Saucar. Así que eso, damos cierre a la charla. Muchas gracias a todos por asistir y los dejamos invitados para nuestros siguientes eventos. Eso. Muchas gracias, Félix.
Muchas gracias a ustedes.
Thank you very much. Y gracias a todos los asistentes.
Bye, bye.